Okay, everybody, this video will cover these next 2 pages of notes. It's technically like chapter 5 material in the book. What we're going to talk about now is continuous random variables, and the uniform distribution function. Okay. Everything we've done in chapter 4 up to this point has been talking about discrete random variables. Remember, discrete numbers are numbers that are countable. So how many books you can cram in a backpack. Some of the other examples, what they say, how many steps you take in a mile. You can count those. Continuous numbers are numbers that are not countable, like all the possible numbers between 0 and 1. There's infinitely many numbers between 0 and 1. Again, things that you just can't technically count. So that actually includes like time and weight. You know, a scale or a stopwatch will approximate around time or weight, but it actually doesn't calculate the exact instant of time or weight. For example, maybe your backpack full of books weighs 30.31312656 blah 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 pounds. The decimal might never technically stop. Anyways, when you're dealing with continuous random variables, it's still this idea when calculating probability, I need to identify the type of random variable I have so that I know the correct set of formulas to use to calculate probability and expected value and all that good stuff. When you're dealing with a continuous random variable, though, it sort of changes a bit how we calculate probability. There's still a formula and all that, but with discrete variables, we tend to think of the height of a graph as being the probability. With continuous random variables, we see that we actually have to treat it as the area under some sort of curve as the probability. So we'll get into all that. So again, let's just remind ourselves, when someone asks you, what is a distribution, what 2 things are we going to tell them? Remember, a distribution includes all possible outcomes that can occur from some event, and then it's going to be the frequency or probability of each value. Since we're talking about a probability distribution, then it would be the probability of each event occurring. Okay. So just to remind ourselves here, they say, example, create a table and draw a graph of a distribution of outcomes when rolling a die. So we need to assign a random variable. Remember, so maybe I'll say let x equal the outcome I get when rolling a die. Okay, so two situations. Well, what am I saying? There's 2 things I gotta write down. I gotta write down every possible outcome that can occur. I can get a 1, 2, 3, 4, 5, or a 6 when I roll that die. And I need to list the probability of each outcome occurring. The probability of getting a 1 would be 1 out of 6. The probability of getting a 2 is 1 out of 6. 3 is 1 out of 6. 4 is 1 out of 6. They're all 1 out of 6. I hope that makes sense, right? Because on a fair die, you know, we're saying we've got 6 numbers on here, right? And so for any given number, the probability of getting one of those numbers is 1 right option out of 6 possible numbers on the die. And if I were to graph this probability distribution, if I were to kind of list out all my outcomes, and write down the probability of each event occurring, you know, if I create a little histogram there showing the the relative frequency, which is just the probability, what I end up getting is a uniform distribution in this case. Everybody has the same probability of occurring, right? This would be the chance I get a 1, 2, 3, 4, 5, and 6. Okay, and so the probability of those are all the same. They're all at 1/6. So if I'm going to add an example here. What if I wanted the probability of x equaling a 1 or x equaling a 2? Remember how we handle an OR statement? Don't I add those up? So that'd be the probability of getting a 1 plus the probability of getting a 2. There's no overlap. I can't be both at the same time, so I would simply just add those up. I don't have to remove any double counting. The probability of getting a 1 is a 1/6, and the probability of getting a 2 is a 1/6. So I end up with 2/6, or 1/3 if you reduce it. Okay. And if you notice, take a look at that. If I just shade that, the probability of getting a 1 or a 2, if I just shade that space on my graph, you might notice that if I were to ask you what's the area of this box that I just shaded or highlighted, remember the area of a rectangle, isn't it length times width? Or length times height, however you prefer to say it. So this thing has a length of 2 units, right? If I'm thinking length times height, maybe I'll say, the length would be from 3 minus 1, right? 3 minus 1, that's the total length there. And that has a height of 1/6. So that's a length of 2, a height of 1/6. I get 2/6. It's the same answer I got by doing the probability. And so this kind of clues us in that actually we're going to see that the area under your distribution curve is the probability. Now, when we're dealing with discrete events, again, discrete numbers are countable. I didn't really need to utilize this idea to find probability. I can just add them up individually because there's only a finite number of things that I would need to add. So I could count them up and add them up. When we start talking about continuous random variables, though, there's going to be infinitely many values in between any of these numbers. And in other words, I can't add them all up by hand. There's infinitely many, and I can't do that. So to calculate probability, we're not going to simply add up each individual piece. There's too many. Instead, I'm going to go about it this way. And I'm going to say, okay, well, I can also interpret probability as the area under this probability distribution function. So that's what we're getting to here. That is how we handle probability of continuous random variables. It's the area under the curve. Okay. So it takes a minute to get used to this, but hang in there. You'll get it, and we'll start to do a lot of examples, and we'll see, hopefully StatCrunch will help. We'll see that it's really not hard to calculate these, okay? So just hold on. So they use a lot of new terms here. A density curve is simply a graphical representation of a continuous probability distribution. Oh boy. So I guess imagine the same sort of scenario that you're flipping or you're rolling a die, but suppose somehow we have a die that has like infinitely many sides. So not just a 1, 2, 3, 4, 5, or 6, but infinitely many numbers you can roll. Okay, and so if I think of the chances of rolling that number, or that number, or that number, or that number, or that number, what I'm getting at is you would have so many values infinitely close together that what you end up creating is just rather a smooth, continuous curve. And there's technically infinitely many data values within here. Okay, so here I'm still going to write out all my values, that's for sure. And here, this is still a very important height to be aware of, but it's no longer going to be simply that the height of this determines the probability of landing at this particular number, whatever it is. That's not going to happen. In fact, the probability at any one specific number on this die with infinitely many sides would actually be 0, okay? Because you're trying to get a 1 out of infinity choices. That's 0. 1 divided by infinity is so tiny that we call it 0. So when you're dealing with a continuous random variable, we actually don't have individual... sorry guys, hold on one second. Sorry about that, guys. My daughter came in. She said, "Are you doing work?" I said, "Yeah." She said, "Can I do my princess work?" So anyways, sorry. I'm not quite sure where I left off, but the idea I'm trying to make is, or the point I'm trying to make is that no longer for a continuous probability distribution function, no longer is the height of the curve what determines the probability like it was here. It's instead the area under the curve that's going to determine the probability. I still need to know what that height is because that's going to be used to determine, the area of this box. It's length times width, or length times height. But it's no longer itself the probability. The area under the curve is. Okay. I think this will make some sense once we get our hands on some actual examples. So, two things are going to happen. We know that for any probability distribution function, don't all the probabilities have to add to 1 or 100%. Okay, so what that means is that if area under the curve is how we're now calculating probability for these things, the total area under the curve has to be 1. And we also have that every point must have a height greater than 0. So in other words, my curve is always above the x-axis. There are no negative heights because that would imply negative probability, which we said we can't have. So one of the first and easiest types of distributions to explore that's a continuous distribution of a random variable is the uniform distribution. And that's actually what we're looking at up here. So there's 3 things that make a distribution continuous. So remember, given various scenarios, one of the goals of statistics is to say, okay, looking at these conditions, we must determine what type of a distribution do I have. That's going to then determine which set of formulas do I use to calculate probability and expected value. So here's the criteria to fit the uniform distribution. 1 is the random variable must be continuous. 2, every probability has to be the same. Okay? The probability of every single event has to be the same. And lastly, the density curve is going to end up being rectangular in shape. And really that's because of step number 2. Okay? So what we're going to get is if I were to map out the density curve, which again is just the visual graph of the probability, it's just like what we did with histograms, showing relative frequency, which is probability. It's just here we have a continuous random variable. So there may be between here and here, there may be infinitely many data values, say between A and B. There is some really important height that we're going to need to establish, and that right there is going to be my uniform distribution function, and the area under the curve determines probability. Okay. Remember, this total area is 1. That's what's going to help us determine H. Okay, hang in there. You might be thinking, what the hell has Ben talking about? Let's just get some examples under our belt, and I think this is not going to be too painful, okay? So, take a look at this example here. It says that for New York City weekday late afternoon subway travel from Times Square to Met Stadium, you can take the number 7 train that leaves Times Square every 5 minutes. Given that the subway departure schedule and arrival of a passenger, the waiting time is between 0 and 5 minutes, and all waiting times are equally likely. Given all that, draw the density curve. Okay, let's try and wrap our heads around that again. They're talking about taking a particular subway that goes from Times Square to Met Stadium and it departs every 5 minutes. Okay, so imagine you're going to wait for a train or a bus. When you show up at the train or bus station, it's just kind of say the bus or train comes every 10 minutes and you just show up at random. You kind of don't know how long you'll be waiting. You know it's going to be less than 10 minutes if you miss the bus, but is it going to be 2 minutes, 3 minutes, 5 minutes? That's the type of probability questions we can answer here. What I need is the density curve to figure that out. So down here, I'm going to put on the horizontal axes my wait time. And notice they told us that x is the wait time. The waiting time x is between 0 and 5 minutes. So between 0 minutes and 5 minutes is the total time that I would have to wait for this train. Okay. So I could wait any time in between here, maybe 1.1 minutes, maybe 3.9752 minutes. Okay. There's infinitely many times technically between 0 and 5 minutes. So before I can calculate probability, this is an important piece. All the waiting times are equally likely. Okay, so I guess before I jump into it, we should verify that this is actually fitting the uniform distribution. If you look back at the previous page, to follow the uniform distribution, it had to be continuous. Ours is, because we said that there's infinitely many wait times between 0 and 5 minutes. The probabilities of each value or of each wait time is the same as every other wait time, which they tell us that's true in the problem. The wait times are all equally likely. So it's just as likely that you'll show up and have to wait 4 minutes as it is that you'll show up and only have to wait 1 minute. It's just random luck of the draw. And if that's the case, your density curve is going to come out to look like a rectangle. It's going to have some height that we'll have to determine. But because all the probabilities of every number here is the same or is equally likely to occur, the height at every point is the same. Okay. Now, before I can do any probability, I have to know what is that number h. Okay. Because again, look what they're going to do. They're going to say find the probability that a randomly selected passenger has a waiting time greater than 2 minutes. So they're asking me what's the probability that your wait time is greater than 2. Okay. Well, I could find 2 minutes on here. That would be somewhere around theirs, maybe 2 minutes. And wouldn't this be all the wait time that is greater than 2, right? Between 2 and 5 minutes, that whole area there, that area is exactly the probability I'm looking for. Well, that area is easy to find. It's length times width, right? Or length times height. That's a rectangle. So I know the width. I could calculate that. From 2 to 5, I could figure out how far that is. But I need to know the height of this thing. Okay. So let me just take a step back here. I know that in general, this whole area, right? Doesn't the whole area total to 1, right? I know the whole area has to total to 1, okay? So if I'm thinking the area equals 1, I know area of this rectangular shape is length times height. That's got to equal 1. And I know the length, the distance from here to here is 5, right? Because it spans from 5 to 0, or 0 to 5. You can always take the end point minus the starting point to get your total distance. So this is really 5 times h is 1. So when I divide by 5, I get that h is 1/5, or that's 0.2. So this guy has a height of 0.2. Again, that does not mean that every single number you choose has a 20% chance of happening. Remember, the height no longer means the probability is 20%. If that were the case, you'd have infinitely many values having a probability of 20% that would add up to more than 1. That can't happen, right? In a probability distribution function, all the probabilities must add to 1, not bigger than 1. So that right there, though, helps me to complete this puzzle. Because then what I want to do to answer this problem in part 2 is I need to say, okay, well, there's the 2-minute mark. Again, I was interested in finding the probability of someone showing up to the train station and having to wait more than 2 minutes. Right? That was all this distance right here. That's the probability that you're waiting more than 2 minutes. Well, that probability is just that. My mask is dry? Thank you. Thank you. So the probability that x is greater than 2 would be just this green shaded area. It's the length times the height of that box. You can always find length by subtracting the endpoints. 5 minus 2 will tell you that distance, the length. Times the height, we know the height is 0.2. So this is 3 times 0.2, that becomes 0.6. So when someone randomly shows up to this train station for the train that leaves every 5 minutes, there's a 60% chance they're going to have to wait more than 2 minutes. Okay. So the strategy for these problems is always determine the type of distribution. Okay. So again, this type of distribution is uniform because it's continuous, right? There's infinitely many wait times between 0 and 5 minutes. And all the wait times are equally likely. That's going to give us a rectangular shaped graph. It's a uniform distribution. All right. Let's try this next example here. Actually, you know what? Let me show you how you could calculate these on StatCrunch. So I've got StatCrunch up. Again, if you want to calculate a probability, we're just going to go to Stat, and we're going to go to Calculators. Okay. And then I need to go find the calculator for the distribution I'm working with. In this case, we're doing a uniform distribution. So I'm going to hit uniform. There's the rectangular shape. Now they want to know what's the lower limit and upper limit. So these would be the wait times. I could wait 0 minutes, or I could wait a maximum of 5 minutes. Now notice what happened. It automatically calculated the height of the rectangle for me, and it's at 0.2, just like we found. Then I could use the probability calculator down here to figure out the probability. They wanted to know what's the probability that I would have to wait more than 2 minutes. So I'm going to find greater than or equal to 2. What's the probability x is greater than or equal to 2? 60%. All right, 60%. Some of you might be thinking, okay, well, you said more than, but so that would imply strictly greater than, not greater than or equal to 2. Remember, we don't worry about what's happening right at 2. Right at 2, there's technically no probability because you would have a height, but there's no width to it, right? If you're thinking probability as far as an area, the number 2 creates a rectangle. It's not a rectangle, it's a line, and a line has no width and therefore no area. So our computer program here just uses greater than or equal. It's implying the same thing because it would be no difference if you were to use a greater than symbol or a greater than or equal symbol. At 2, there is no probability. Okay. Hold on a second. That looks really good. Okay. Sorry about that. So, yeah, let's go back to our notes and try another example. Let's try this last one. Okay, so this says that a random number generator on a computer is programmed to select 2 numbers between 1 and 4. What is the probability that both numbers selected are greater than 1.5? Let's imagine what's going on. They say draw a density curve. So let's think about this for a second. I guess we sort of, again, want to wrap our heads around, is this considered uniform? So would this be a uniform distribution? We'd have to first say, well, what is the random variable we're talking about? I think x could be the number randomly generated. Okay, so the question they're asking is, what's the probability that that number x is greater than 1.5? So is this a uniform distribution? Well, I would say yeah, because for one, it's continuous. If you think about all the numbers between 1 and 4, there are infinitely many numbers between 1 and 4. Okay, so it definitely is continuous. Now, the other thing you got to see is, does every number in between 1 and 4 have an equal probability of happening, or are some numbers more likely to happen than others, thereby having more area under it? All numbers are equally likely. I would say yes, because if they're not all equally likely to occur, then it's a really crappy random number generator. I mean, to be a random number generator, the idea is that any number in here has an equal chance of being chosen. It doesn't favor one or the other. Okay. Well, if that's the case, that all the probabilities are equally likely, then our distribution is going to take on the shape of a rectangle, because every number in between here has an equal chance of occurring. Right? So it's not like there should be more or less height, thereby giving more or less area under the curve to any number in particular. Now, to complete this density curve, I have to know what is that height. What is the height of that distribution there? So again, what helps us to do that is, the one thing we know is that the total area here, has to equal 1, right? The area under this curve has to equal 1, just like the probability. That's a really cool mask, Eleanor. Thank you. Okay, hold on. And I'm back. So the probability, where was I going? Oh, the total area under the curve has to be 1. And I know that area is length times height. The length is the span from here to here. Again, you can always find that by subtracting the endpoints. There's a distance of 3 there. And so when I divide by 3, I get 1/3 for the height. That height there is 1/3. Okay. So once I have that, I've got everything I need to calculate probability. Okay, because they're going to give me a target, and they want me to be either above or below that target. And so I'm just going to create a little rectangle that I'm going to look for the area of. So here it says, again, we picked 2 numbers. Suppose the probability of both, find the probability that both numbers are greater than 1.5. So what I'm really looking for is the probability that x, the first number I get, is greater than or equal to 1.5. Doesn't really matter if you use the equal to or not. And the next number, this is written a little weird, is greater than or equal to 1.5. I keep saying greater than or equal, but only writing greater than, again, because it doesn't matter in this case. It's an and statement, so I'm going to multiply these. And because these things are all equally likely to occur, this second guy isn't some sort of conditional probability. It's not like I pulled a marble out of the bag and left it out, therefore affecting the probability of the second one occurring. Every time you hit go on this random number generator, we can safely assume that every number is equally likely to occur. So the fact that my first number was bigger than 1.5 shouldn't have an impact on whether or not the next number is bigger than 1.5. Okay, so let's figure this out. On my graph, find 1.5. That's about right there. Maybe that's the number 1.5. I'm looking for the probability of any number being greater than 1.5. So that's going to be to the right of that number. So in between 1.5 and 4. That's the probability I'm looking for right there. And the probability of that is simply just find the area of that rectangle. Well, again, the area of the rectangle is length times height. So the length would be from 1.5 to 4. If you want to figure that out, you could just subtract them. That tells you the distance between here and here. Times the height, so times a third. Or 0.33 if you want to use decimals. Alright, that's the area for one of those slices there, or for that green rectangle. And then I'm going to multiply by the area of getting another number greater than 1.5. Well, again, that's this isn't a conditional probability. Every time I generate a new number, everybody's equally likely. So this would be the same area, same probability. Okay. So what do I get out of here? Let me see. 4.5 minus 1.5, that's 2.5. This all comes out to 0.694, the whole thing. Okay. Let's double check it with StatCrunch. And actually, well, yeah, let's just double check it with StatCrunch. I should have done these individual. Let me do that real quick. 2.5 times 1/3. Individually, this is 0.833 repeating times 0.833. And then together, I said that gave me 0.694. Okay, let's see what StatCrunch tells us. We should be seeing this for our answer if we do one of these rectangles. So I'll just run through the steps again. You would go to Stat, Calculator, and we are working with a uniform distribution. The lower limit, the lower number that could be generated by this computer program is 4. The upper limit, I'm sorry, is 1. The upper limit is 4, if I recall right. Right? It creates a number between 1 and 4. Yeah. So I'm looking to find the probability of getting a number bigger than 1.5. And there it is, 0.8333, repeating, just like we found here, doing it with area, 0.8333. And again, they just said we've got two numbers doing this, so I need to multiply those probabilities, and that's how I get your final answer of 69.4% chance that both the numbers will be greater than 1.5. Okay. I hope this one went okay. This was kind of tricky. Well, A, I had some distractions, but B, it's the jump from continuous random variables, from discrete random variables to continuous random variables. And so this is always a little bit of it's not hard to do, but it's brand new, all right? And it's a new kind of concept and idea, so it might take a little while to get used to it. Really, from here on out, everything we deal with is going to be a continuous random variable, because most things are. It's usually not discrete that we're interested in, though sometimes it is, but by and large, we want to know how to analyze a continuous random variable. So this is what we're going to be doing for quite a while. Okay, talk to you guys in a bit. I thought I would share the mask my daughter brought in that was all done drying. It's pretty cool. All right, you guys, take care.